From a practical point of view, of course, stick with your ordinary language. And if it would impede the progress of mathematics, for mathematicians to read Mathematics Without Numbers, my book, my goodness, don't let them read it. Not only do they not have to read it, they shouldn't read it because it might confuse them. They're concerned with different things. They want to know, about solving some equation. And I want to avoid talking about numbers.
All right, so welcome everyone to today's interview, where I'm very pleased to welcome Professor Geoffrey Hellman. He is Professor of Philosophy at the University of Minnesota. His work focuses on the philosophy of mathematics, logic, science, and metaphysics. His books include, among others, Mathematics Without Numbers toward Modal Structural Interpretation, Mathematics and Its Logics, Philosophical Essays, Varieties of Continua from Regions to Points and Back with Stuart Shapiro, and others, as I said. He also has many published articles on these topics and more. Feel free to add anything, but with that, welcome and thanks so much for being here, Professor Hellman.
It's my pleasure.
Awesome. So, of course, we're going to focus today's interview on your work in the philosophy of mathematics, in particular on your modal structuralism. But before getting into it, just as a kind of general introduction, so some of the issues that commonly come up in this area have to do with mathematical entities, relations, truths, what are they, how are they true, and so on. If they are, do natural numbers exist, that sort of thing. And so before getting to your preferred approach, as a kind of, by way of introduction, can you give a bit of a brief overview of the different approaches here and maybe some of the history of this?
Well, I'll try. Of course, it's a big topic, and there have been many contributions, starting with the ancients. Of course, I would say that the dominant approach in modern times has been, and maybe throughout the history of Western thought, has been what we call an objectivist, Platonist approach to mathematics. We're talking about pure mathematics now. Going back to ancient Euclidean geometry, for example, it was taken for granted that they were talking not about actual lines in the sand or on paper that could be written, but they were talking about some idealized line that had absolutely no thickness, that had only length. Now, nothing like that exists in the physical world, but mathematically, it made sense to the ancients, and it makes sense to us to this day to talk about a triangle which has line segments as its sides. So they accepted the idea of lines, and even further from experience, points. What is a point in this abstract sense? It has no width, no depth, no length. It's without any dimension, and yet it's something. We represent it in our drawings on blackboards and on paper with a point of the pencil or the pen. But of course, that isn't an idealized point. So, we're indebted to Plato for saying this doesn't mean that we're restricted to talking about physical points. We can still talk about exact, precise, dimensionless mathematical points, or pure geometric points. But they don't live in the physical world. They live in some abstract space. Now, that's a very convenient way of looking at things, and it allows mathematics to proceed as if there were such things. But from a philosophical point of view, there are problems. Uh, we don't interact with any of these things. How do we know that they exist at all? We don't have, they're beyond our experience. We never experience a perfectly straight line. We talk about idealizations, but then if we start talking about ideal objects, where do they live? They don't live in our space. How do we have any access to them? How do we know that they even exist? And that's the problem of Platonism. Now, mathematics gets by without asking those questions. It just proceeds as if there were these things. And then it reasons rigorously about them. And it draws all kinds of interesting consequences from the basic assumptions that they make about such things. And for pure mathematics and applied mathematics, this is perfectly fine. Though applications of mathematics require some account, special account, because how do these ideal objects match up with what we actually experience or have access to in the physical world? But that's a whole separate topic. So the default view is called Platonism. And that's the view that there are indeed these abstract objects, geometric, number theoretic, and for all the branches of pure mathematics, objects that they talk about, so to speak. And so the Platonist just takes for granted that there are such things and proceeds without further ado. But now for the philosopher, and also for the logician who wants to know where does the reasoning start and what are the most basic assumptions, this Platonist view has been seen as quite unsatisfactory from various standpoints. Hilbert is famous for a quote that's attributed to him standing at on a railroad at a railroad station waiting for a train. He said, "It shouldn't matter what we're talking about when we talk about mathematical objects. They could be beer mugs, tables, chairs, whatever. As long as they're interrelated in the right ways, we can go ahead and reason about such things as if that's what we were talking about." So he was saying that the objects of mathematics don't really matter. What is important is the interrelations among the objects. And it didn't matter what the objects were. So that's an idea that is modern, and it's associated with the term structuralism for obvious reasons, because what Hilbert was getting at is that it's the structural interrelationships of things that are of primary interest in mathematics and not the objects themselves. And so that's an intuitive idea and an intuitive break with Platonism, but it doesn't really go far enough. It's just a suggestion. What are relations? And how do we reason about relations? So the idea of modal structuralism, well, I don't know if you want me to jump into that at this point, but maybe you have a further question on this, on these introductory remarks.
Yeah, no, but that's a great sort of introduction overview. Yeah, and then of course you gave a sort of brief introduction to structuralism, but there's many different types of structuralism,
right? Like
the kind of sui generis structuralism, set theoretic versions, categorical versions. I talked with Michael Resnick. I'm going to bring him up later. He has a particular view. So yeah, maybe at this point, if you want to just kind of get into your version and separate it or distinguish it from the other kind of structuralist approaches that have been on offer.
Right. So I was strongly influenced by, well, several of my predecessors. I already mentioned Hilbert. That was very important. Prior to Hilbert was Richard Dedekind. And I learned about his work from Howard Stein, a wonderful philosopher, mathematician, scientist in his own right. Used to be at Columbia and then moved to the University of Chicago, where I got to know him because I was at Indiana University at the time. And I would visit friends and like David Malamud in Chicago at the University of Chicago. And I sat in a class that Howard taught. And he was talking about this great essay of Dedekind's that I had not yet read. It was called, it's translated in a Dover paperback called The Nature and Meaning of Numbers. And that, it's published in a Dover paperback along with a more famous essay of Dedekind's. Both of these translated into English, originally in German, of course. The other one on continuity and irrational numbers, which is Dedekind's famous reconstruction of the real number system, not the natural number system, but the real number system corresponding to the points on the geometric line. Think of the x-axis by infinite to the left and to the right, and think of all the uncountably many points on the line. Dedekind is most famous for his way of defining these points or real numbers in terms of more basic things, like the rational numbers, which are just all the fractions that we can write down that we learn about in elementary school. A half, a quarter, an eighth, a 16th, et cetera, et cetera. And those are called the rational numbers. They're only countably many, but they're dense. They're densely ordered, unlike the natural numbers, which are also countable, of course, 0, 1, 2, 3, and so on. And then the integers, where you put minus signs in front of all of them. And so you can go to the right and to the left along, say, the x-axis. And then you move to all the fractions. That gives you the rationals. And Dedekind famously in this first essay said a real number or an irrational real, the rationals count as reals, but the irrational numbers are defined by partitions. He called them cuts. So a cut in the rationals would be a pair of sets. Together, they exhaust all the rationals. They don't overlap, so they don't intersect. So there are no rationals in common. But then there are three kinds of cuts. There are those where a rational, say, 0 itself, belongs to, say, the right half of the cut. That is, all the rationals greater than or equal to 0, and doesn't belong to the left half. And then the left half will have no largest, because those will all be negative numbers, no largest rational. And then vice versa. You could include 0 in the lower section of the cut, and then the upper section would have no least element. But then he said, those are the cuts that correspond to rational numbers, but then there's another type of cut where the upper section has no least member and the lower section has no greatest member. And that will define an irrational number. So he actually gave an explicit definition of irrationals. And then he showed that they have this structure of being dense in the rationals and vice versa. You can get as close as you like to one type from the others. But then there was the question, well, now what if you try to repeat this cut process? Will there be any cuts in the rationals plus irrationals? Call those the reals. Will there be any Dedekind cuts where there's no least member of the upper section and no greatest member of the lower section? And the answer that Dedekind was able to give is no. There are no further irrational, if you will, numbers. The reals are complete. So he gave a meaning of completeness. That's the more famous essay. But the one that Howard Stein was focusing on was the second essay, which is called in German, Was sind und was sollen die Zahlen? Now, that's translated in the Dover edition as the nature and meaning of numbers. But that's a very inexact translation. Was sind means what are. Was sind und was sollen die Zahlen? So what are the numbers, and was sollen die Zahlen? What should be the numbers? Well, that's a very strange question. Actually, there's a more colloquial expression that Howard Stein used. Was soll das means, what's the point of that? So something like, what purpose do they serve? Does that serve? Was sollen die Zahlen? What's the point of talking about numbers? Something like that would be. So it's hard to translate Dedekind's title of this great essay into English. But what it does is it points out that the foundations of arithmetic are a mess. Nobody has clarified what numbers really are. There are many different conceptions of the natural numbers. It's the most elementary structure in classical mathematics that is not finite. It's what we all learn in grade schools. We learn before grade school when we learn how to count. So the counting numbers were his focus. We now call those ordinal numbers rather than cardinals, which are cardinal numbers are often identified as the same objects, but they serve a different function, as it were, which is they measure the size of collections. So if you're talking about size, you're talking about cardinals. If you're talking about place or position in an ordering, then you're talking about ordinals. So Dedekind's focus was on ordinals. And zero, what do you do about zero? Well, you can stick it in there for convenience. It's better thought of as a cardinal than an ordinal. But if you were to start counting with zero, everything be moved by one, right? Then if you got up to 3, you'd really have counted 4 things if you use zero. But anyway, that's just not worth focusing on at this stage. But Dedekind was thinking of the ordinals. Well, in this essay, he tries to lay a firm foundation for reconstructing these numbers. But he doesn't treat them as individual numbers. He treats the whole structure. So what he does is he defines what he calls a simply infinite system. Now, a simply infinite system it's defined by the following. There's an initial element that is not a successor of any element. And then every one of these elements has an immediate successor, or we'll just say a successor, a unique successor. And any two different numbers have different successors. And then finally, there's this principle that he calls induction. To show that something holds of all the numbers, it suffices to show that it holds of the smallest of them, which he calls 1, and that for any number that it holds of, it also holds of the very next number, the successor. Once you've shown those two things, then you've exhausted all the numbers. Then you've shown that the property in question holds of all the numbers. That's called the principle of mathematical induction, not to be confused with scientific induction of the sort that the empiricists talked about, like John Stuart Mill, before him, Locke, Berkeley, and Hume, where you were proceeding from the particular to the more general. Right? That's scientific induction. And that is not logically a valid move. It's inductively often, sometimes a warranted move, if you kind of know what you're talking about. Like, this stone is hard, this other stone is hard. We're going to leap to the conjecture, not a certainty by any means, but that all stones are hard. Of course, some stones are harder than others. And then we get into more interesting mineralogy. But that's a different kind of induction, the most familiar kind. This is mathematical induction, which is a perfectly logically, deductively correct move to make in the context of a system of the sort that Dedekind was calling a simply infinite system. We might call it a natural number type structure. Okay, so that's the idea of a structure of elements characterized by these conditions. There's an initial one, everyone has an immediate successor, two different ones, two different successors for any two, and that principle of mathematical induction, that it suffices to show that all the numbers have a property if the least number has it, and if the property holds of the successor of anything that has it. And so then, armed with that definition of a simply infinite system, Dedekind did two remarkable things. One of them that we don't think is kosher, and the other which we celebrate as a great theorem. The first thing that we don't recognize as kosher, pardon my Yiddish, it's one of the few Yiddish words that I know. I'm not observant. The first thing he did was to try to establish that simply infinite systems exist. Now, you might think he could have talked about space-time points or regions, and he could have. He could have said, look, we all recognize things like an interval of space-time, say a straight line from point P to point Q, idealized as a Euclidean straight line, but it could even be physical. But then he's going to say, within this, we could construct a simply infinite system. We could take the leftmost point and then take half the distance to the next point, to the next end point. So we have this finite interval. So we have now 0 and 1/2. Now we could get 3/4, then 7/8, 15/16. You see what I'm doing. And you can proceed that way ad infinitum. And that would be a simply infinite system. You would never get to 1. You would just be all the binary rationals, inclusively between 0 and not, including 0, but not including 1. You get closer and closer to one. But Dedekind didn't do that. He said he wanted to work just in this kind of solipsistic way. He said, the objects of my thought form a simply infinite system. Because he had this idea that you could iterate the idea of the thought of something. So I could be thinking of a tree, maybe in Palm Springs, since it's still a little chilly here in Minnesota. I'm thinking of a tree, but then there's my thought. I can reflect on the thought of that tree, which is different from the tree. But then I can iterate that. I could say, I can think of the thought of the tree, and so on. And that would be a simply infinite system. So that was Dedekind's first, he called it Theorem 66, I think. That was the first of the big theorems, existence. And then there's the question of uniqueness. So now this existence proof is very, very strange. It goes way outside of mathematics. It gets into mental activity. And it's not even clear that it makes sense to talk of the thought of the thought of the thought more than 3 or 4 times. I run out of steam at about stage 4. I don't know what I'm talking about after that. Maybe you can go further. But anyway, that's Theorem 66, ill-fated though it was. But then there's the much more important and celebrated and mathematically correct theorem that we make perfect sense out of, which is that if you have 2 simply infinite systems, there's a 1-1 correspondence between them that preserves all of the structure. It preserves the successor structure. They both have initial points, but no greatest points. They go on ad infinitum. And there's a 1-1 correspondence between them. You map the smallest, or the starting point of one to the starting point of the other. And then you make sure that you map the successor of any point to the successor of the image of the first, of the point from which you're taking the successor operation. And that gives you what's called an isomorphism, a 1-1 correspondence. It preserves the successor structure. And then from successor, as Dedekind showed, and we all learn eventually if we do anything in foundations of mathematics, you can define the operations of addition, multiplication, exponentiation, all ultimately from the successor relation. So all you need is the successor relation or function to define the structure, because you get this beautiful isomorphism theorem. So modern logicians would say the axioms. All right, so now what about axioms? So Dedekind didn't say that those postulates that he laid down, they're really defining conditions on what he was going to mean by a simply infinite system. He didn't call them axioms, but Peano did. And that was much more convenient. Peano was a mathematician, important one, Italian, living late 19th, early 20th century. He read Dedekind's essay and was very impressed, and he took over Dedekind's defining conditions on simply infinite system, and he called them axioms. And then he wrote his own essay developing this axiomatic system. That got more attention than Dedekind's essay. I don't know if there's some history, maybe Troy, whether there's some history that explains why the Peano essay became so much better known For many decades, we've known these Dedekind axioms, Dedekind defining conditions, as the Peano postulates or Peano's axioms. And we call the system of those axioms PA instead of D. I always refer to PA now as DPA. Interestingly, Peano, on page 1 of his famous essay, has a footnote, his first footnote. And he says, I got these axioms from Dedekind. And he cites the Was sind und was sollen die Zahlen that I was just talking about. So anyway, Dedekind's structuralist ideas kind of got lost in the tradition because you had the Peano postulates, which cried out for an explanation of what is the subject matter of these axioms. And they're called the natural numbers. And that's a particular thing. That's not just any old simply infinite system. It's a particular abstract one that's really infinite. But how do we come to know it? These are abstract objects. They're not located in space and time, like pebbles on a beach or anything like that, or atoms in space. We don't know if space actually is infinite in extent. If you go far enough out, you circle back on yourself. These are big questions of cosmology. Anyway, mathematics clearly should not depend on that. Every child knows that the arithmetic of whole numbers concerns that there's no largest number, that you can go on forever and still find more numbers. So we're talking about something abstract. And Russell, who made Frege's work famous, and Frege was a contemporary of Dedekind's, who wrote his own system of foundations of arithmetic. Dedekind was a Platonist. I'm sorry. I should have said Dedekind is a proto-structuralist, but Frege is clearly a Platonist, and so is Russell. Russell toyed with the idea that the Dedekind axioms could be thought of as applying to a multitude of systems, and that we were just reasoning about what they had in common. But he said that would be somehow not satisfactory. I never understood what the problem was supposed to be. He thought that it was better and maybe necessary to have definite objects that you were talking about, rather than generalizing over all structures of a particular type. So Russell's famous Principia Mathematica proceeded to treat the numbers as particular abstract objects. And so Platonism crept back in after Dedekind. It was there with Frege, and Russell took it over from Frege and had his own very arcane and cumbersome type theory. I'm not going to go into that here. But anyway, the structuralist message that was, shall we say, suggested in Dedekind's great essay, and which was also further promoted by Hilbert, especially in his informal remarks at a train station, fell into kind of disuse or lack of development. So when I was in graduate school, I don't recall any of my logic or philosophy of mathematics professors talking about structuralism. The first use of that term in connection with the philosophy and foundations of mathematics was Howard Stein's. That was many years after I had had my PhD. Well, not many years, but several years. And Stein said this is a kind of early version of structuralism, but it clearly needed further development. And so that was one of the things that led me to think this needed to be done to give a more rigorous account of the structuralist insights. That when we give axioms in mathematics, we're not talking necessarily about particular structures, but are talking about what would be the case for any objects that are suitably interrelated according to the defining conditions or axioms that we're interested in. So that was one major influence, Howard Stein and Dedekind. Another major influence was Hilary Putnam, a great philosopher of the 20th century, who was one of my advisors in my graduate doctoral work. Putnam wrote an essay in the 1960s when I was still a student of his, 1967 to be precise, published in the Journal of Philosophy, I believe. Has a misleading title. It's called Mathematics Without Foundations. In this paper, Putnam argued that it would be helpful in understanding the foundations of mathematics to make use of the notions of necessity and possibility, what are called modal, alethic modalities, in connection with pure mathematics. So he wanted to say that mathematics studies possibilities. Possibilities of structures, for example, that go on and on. So he was particularly interested with some of the problems with set theory. So set theory, pure set theory, was developed first by Zermelo in the first decade of the 20th century. Zermelo was a great mathematician, scientist, who was, I believe, a student of Hilbert's. Hilbert was considered one of the two greatest mathematicians of his day, Poincaré being the other. Zermelo was one of his greatest students. He actually did work in physics, but he's most famous for his work in Foundations of Mathematics. He came up with the axioms of modern set theory called ZFC. Actually, Zermelo gets credit for all the axioms but one, and he gets credit for the C, which is the axiom of choice, which says that if you're given an infinite family of non-empty sets, there's a function that picks out an element, a single element from each set. The existence of that function is a strong mathematical assumption. It can't be derived from the other axioms. And then there's, so that's Zermelo with choice. Where does the F come in? F is for Frankel. Frankel added another axiom that Zermelo liked, said he should have added, but had not done so, had neglected to. So, and that's the axiom that says that the structure of sets goes on and on beyond what could be measured by any set. So the idea is that you start the structure for a model of set theory with a single element, which is called the empty set. So this is already kind of Platonistic, right? A set that doesn't have any members? What? Like everybody in a school class leaves the building and we say, well, there's still a class there. No, everybody's gone. Well, there's the empty class. And it's always the same no matter what left it. There's only one empty set. That comes out of another axiom called extensionality. Any two sets that have the same members are really only one set. There aren't two different sets with exactly the same members. So you start off with that, and then you proceed by taking all the subsets of earlier sets for your next level. So you have levels, 1, 2, 3, 4, and they go on and on. How far do they go? Very far. For Zermelo set theory, you get an infinite level because there is an axiom of infinity. So after level 1, level 2, level 3, you're getting fatter and fatter because your contour back in the 19th century proved a fundamental theorem in set theory that if you take any set, whether it's empty or not, and then consider all the subsets of it, you get a larger set in the sense of cardinality. That is, there will be no 1-1 mapping from the original set into and onto the what's called the power set, the set of all subsets. Even the empty set has a power set because all the subsets of the empty set consist of they consist of the empty set itself and the set of the empty set. That's a singleton. So the singleton of the empty set is a subset of itself. Every set is a subset of itself, trivially. A subset is a set that such that anything that belongs to it belongs to the set of which it's a subset. Well, of course, the empty set is a subset of itself. So you got one thing now. Now we take the power set of that, the set of all subsets. Well, now we've got the empty set and we've got the set of the empty set. And so now we've got two things. And so now we've got two. And now we take all the subsets of that, we're going to get four things. All the subsets of that, we're going to get 2 to the 4th, and so on. And that's 16. And up we go. And then we go into the transfinite, because so Zermelo has an axiom of infinity, that there's an infinite level. We'll come back to that. And then you keep going after that. You get larger and larger and larger sets. But how far does it go? Zermelo didn't have any principle at all on the height of a model of what was called Zermelo set theory, even if you had the axiom of choice. The axiom of choice doesn't take you up any further than one more level. You're talking about functions on given sets. Those are sets of ordered pairs of given sets. And so you're only one more level up. And so Zermelo doesn't have any trouble going one step higher because he has the power set operation. But if you're asking, you can go up to the first infinite level, and then you can go up to the second infinite level. That's omega times 2. Does Zermelo set theory require that there are sets beyond that? Answer, no. All the sets within up to, but not including, omega times 2, form a model of ZC. Okay, it's assuming the axiom of choice is a model of Zermelo's set theory. So Frankel comes along and says, look, we want an axiom that will make sure that we can go beyond that. We don't want any stopping point that's kind of easily reached. There should be no stopping point. And so he proposed a very interesting axiom. He said, look, take a set. It doesn't go any higher than the highest member, but it can be very fat. It can be very wide, in the sense of taking sets that are formed at later stages than earlier sets, right? And so you can have a fat set. And now Frankel had this insight that Zermelo accepted right away when he saw it. He said, now let's take this fat set and turn it on its end so it's going longitudinally straight up. And now let's try to spread that out as much as we want. So you can go, by bigger and bigger steps to get to the next element. He wants to say, look, that whole hierarchy that you are trying to construct there, you're trying to spread out this fat set to gain height. He wants to say the universe goes even further. So the universe of set theory, on Frankel's and Zermelo's view, goes higher than can be measured by its width at any stage. So there's no limit to how fat the structure can get. But whatever fatness it has, its height is even greater. So now we're getting somewhere from the point of view of a conception of the universe, a universe adequate for set theory. And that's Zermelo-Frankel set theory with the axiom of choice. That's very pictorial. You just draw a big V, and it goes higher than it is wide. So that's the explanation, the metaphor I learned from Howard Stein. He said, the axiom of replacement says that the universe of sets is higher than it is wide. Okay, this is fine. Now, we skip to 1930. Should I keep going on this vein? This is kind of build up to why I went modal.
No, I actually find it really, really fascinating. I didn't know a lot of this stuff about the history, so maybe it's not all super essential to the view you develop. But yeah, if you want to keep going, I mean, it's very
so I'm going to get to where modal structuralism comes in. This is all essential background, though, to understand it, and where Putnam was coming from. So fast forward to 1930. Zermelo has a second paper on set theory, as important, maybe even more important than the first. And it's called Über Grenzzahlen und Mengenbereiche, on boundary numbers and set domains, neue Untersuchungen in der Grundlagen der Mengenlehre, new studies in the foundations of set theory. So, über Grenzzahlen und Mengenbereiche. And Zermelo had this very interesting idea, which was that even with the Zermelo-Frankel axioms, you have this incredibly large universe of objects called sets. He wanted to say, there's no stopping point. There's nothing to prevent you from building another model of ZFC on top of that and going up beyond that again. So you could stack these things. And he had this idea that it goes on ad infinitum, there's never, it's a series that's never completed. It's like an infinity of infinities. And he said he thought that this helped resolve paradoxes of set theory, because when you think of this fixed universe view, that there's just one universe of sets, well, then you get this problem. Well, what about the class of all of those sets? Why isn't that a set? Let me say, oh no, we can't call that a set because that would lead to a contradiction. Because then there would be its power set, which would be larger than itself. But if it's a set of all sets, it can't be larger than itself. And so you got a contradiction right away. That's called the Borali-Forti. Well, that's not. That's just that's one of Cantor's paradoxes of a universal set. So Zermelo said, well, instead of ruling out the collection of all sets as a set, we could take it as a set, but in a higher model. So there can be an infinity of models stacked on top of one another, and then you could take at any stage, you could take infinite stacks going, each of which made up of structures that large, and so on. There would be no larger structure, and you would never have to deal with this question of the collection of all sets, because the sets would go on and on. Now, Putnam comes along, and he has this idea we should talk about possibility in connection with set theory. And he said he had this principle called the extendability principle, which is any model of set theory, no matter how large, could be part of an even larger model that goes up even higher. They're equally fat at least the first part of of any structure that extends. The first one is going to be preserved, and so you've got a fatness there, but then you go up and it gets even fatter. But you are always going, it's always possible to go further. Now, if we have that idea, so Putnam put it graphically, he said, it's always possible to extend any model of set theory to a higher or larger model. And then he said, even God couldn't make a model of Zermelo set theory that it would not be logically possible to extend to a large one. So that's, I don't know if Hillary was religious, but it was a very strong statement. And it made the point. These models go on, and there's no contemplating any end. Now, the problem with Zermelo was construction, which Putnam, I don't think, knew about because he didn't ever refer to it in his paper, although he had this picture of ever increasing larger models of Zermelo-Fraenkel set theory. He never referred to Zermelo, but when I looked at this, I realized there's a problem with Zermelo's construction because he doesn't have this idea of possibility. And that is, it makes sense in the framework, in the logical framework of Zermelo is working in implicitly, that there be such a thing as a class of all the models, even if there's no greatest model. It goes on and on, like the natural numbers. Just as you have the class of all the natural numbers, that's taken for granted. Well, here you could have the class of all of Zermelo's models. What's to rule that out? Second order logic, if you formalized Zermelo in it, would deliver you this class. That's one of the axioms of second order logic. So, but if you combine Zermelo's insights with Putnam's, then you get a modal structural view of extendability. You get this idea that when you form a class of models, you have to be within a model to do so. There's no standing outside all the possible models and thinking of all the possible ones as a single object. That makes no sense, because there you'd be reaching into other possible worlds that don't exist. They're not all in the same world. See, as long as you stay in the same world, you're stuck. You're always going to be able to embrace whatever you've got. And then you can ask, well, why can't we go further? Why can't we take the power set of that or power class? Call it a superset if you want. Call it a super duper set or a super de-duper set, as Barney the purple dinosaur would say to the children when I was a dad of a child watching Barney. That was always fun, a super de-duper, something or other. You could have super de-duper sets. But if you're working with Putnam's picture and you have these modal operators around, logical necessity and possibility, which Saul Kripke developed semantics for, you have the semantics of possible worlds. Well, you're in a single world when you talk about some mathematical structures. And the idea is you can only form collections within a world. You can't collect what doesn't exist. That's kind of axiom one of modal structuralism applied to set theory. You can't collect what doesn't actually exist, or you couldn't collect at any world what doesn't exist at that world. You could talk about the possibility of collecting some other things in another world, but then you'd be living in that world. You would have more things, more collections, but you couldn't there collect anything that could exist from that world's perspective in some other possible world where there might be more sets or things of any sort. So you can only collect within a world. You can't collect across worlds. That makes no mathematical or logical sense from this perspective. Now, there are logics, intentional logics, that allow you these trans-world collections, but we're just ruling them out as not really making sense when we think about mathematical structures. So if collecting is world-bound, and if talking about some objects plurally is also world-bound, then we get a real advance by combining Putnam and Zermelo. And that's what I did in the second chapter of Mathematics Without Numbers. I laid out how this all works and can be made sense of. And then, so you have this modal extendability principle. Necessarily, given any structure modeling ZFC, it's possible that there is a more comprehensive structure that also models ZFC. And this way we get a whole hierarchy of the smallest of the inaccessible cardinals, the so-called strongly inaccessible cardinals. So it takes you into higher set theory. It motivates at least the small, large cardinals that are the kind of first step in the mathematics, the higher mathematics of set theory, modern set theory. So this is a good place to pause and answer further questions or shut up for a while.
That's really excellent. I mean, I really like that overview. So, where to go from there? I mean, yeah, you did talk a bit about this sort of indefinite extensibility as a sort of feature of your approach, because you've talked about in writing how, well, there's other approaches, even other structuralist approaches, which on your view get that wrong. Certain set theoretic approaches, and
yes,
right, and those may also fail to treat set theory itself in structuralist terms, which could be another issue. So a lot of things came to mind. I did want to ask about, what's the further kind of more sort of motivation for this view over maybe what about other structuralist views? I mean, maybe there's some that others can get around this issue. I guess you've been talking about this, but maybe you want to go on that a bit.
Sure. So clearly this modal structuralist picture with the indefinite extensibility of structures differs from a Platonist version of structuralism that my dear colleague and co-researcher Stuart Shapiro has developed, which he calls anti-REM structuralism. I believe that Michael Resnick developed a version that is somewhat similar but different, that he calls a science of patterns. But the idea is to take reference to mathematical objects at face value. My modal structuralist account, when you get into the nitty-gritty, is kind of nitty-gritty. It looks too technical to work with. It's cumbersome. You have to translate everything into the language, the pure language of what's possible and what's necessary. And you have to do this very carefully with the right, you have to keep track of your quantifiers for all, and there is, and precede each one of them by the right modal operator and so forth. And it gets kind of technical and messy. Now, I do have ways of responding to that to simplify it, but that's one of the motivations for sticking with what's called a face value reading of mathematical theories. So talking about the natural numbers, we take at face value the use of these terms, these names, 0, 1, 2, 3, so on. So like Frege, we could define them or we don't have to. So Stuart Shapiro talks about a certain kind of a privileged structure, which has the natural numbers conceived as particular objects in this idealized structure. The number 1, the number 2, the number 3, and so on. Well, he would start with 0, 2, probably. Cardinal numbers. So he calls it an anti-REM structure. It's kind of achieved by abstracting from all particular structures or systems. He calls them systems. Suppose you had a beach suppose you had a planet that actually went infinitely far in space. And then you had posts along it. So you could talk about that structure as modeling the natural numbers. Or take a space-time interval that's finite and divide it into smaller and smaller pieces like Zeno's paradox, right? You've got a half, but first you have to go to half of a half, that's a fourth, then an eighth, 16th, 32nd, and so on. So here you've got an infinite sequence of points or little subintervals if you want. And you could take that as modeling the natural number structure, leaving out the last point. I did it backwards, starting at the end point. So this was the the way of thinking about it. So how could you get started? Because you have to go over an infinite number of places before you can take one step. So that looks like a paradox. Well, but the point is that this is a model of Dedekind-Peano arithmetic. If you leave out the last point, which was our zero starting point. And there are infinitely many other actual models of it. So the idea is we abstract from that. We say, what do all those kind of quasi-physical models have in common? Geometric models, if you will. Well, what they have in common is reflected in this idealized anti-REM structure. So that's the idea. It's a two-stage process. You start with your experience, then you think of idealized systems where you talk about points and distances going on ad infinitum, getting infinitely small maybe, or infinitely large if you've got the space available. And then you talk about moving to an abstract realm of an anti-REM structure. And so that's the picture that Stewart developed. And that's a different kind of structuralism. That's a Platonist structuralism. And it's very different from the modal version, because the modal version allows you to get by doing all the mathematics you want without ever pretending or committing yourself to the existence of any abstract objects. You just talk about the possibilities of enough things satisfying certain conditions which you can write down on a piece of paper. And so the difference being the modal structuralist eliminates the very term natural number or rational number or real number or even set. In terms of variables, that could be anything as long as they stand in the right relations to other things. That could be anything. It doesn't matter what the objects are, as long as they're interrelated in the right ways. That's a very different picture. And it means doing violence to ordinary language if that's what you want to hold on to. So I say from a practical point of view, of course, stick with your ordinary language. And if it would impede the progress of mathematics, for mathematicians to read Mathematics Without Numbers, my book, my goodness, don't let them read it. Not only do they not have to read it, they shouldn't read it because it might confuse them. They're concerned with different things. They want to know, about solving some equation. And I want to avoid talking about numbers. So they're totally different interests. There's no reason for them to get involved in my business. And I'm certainly not saying anything about how mathematics should be practiced. That has to be made clear. And I'm sure that Hilbert wasn't either when he suggested, the objects could be beer mugs or cards or whatever. Right? So there's a comparison. So if you're talking about what's closer to ordinary usage, anti-REM structuralism has it all over modal. You take the language at face value. It seems that we're referring to numbers. We are referring to numbers. That's fine. And there are all these different anti-REM structures. Oh, well, I don't know what happens when you get to set theory, though, because there it seems that we have indefinitely many structures. Maybe Stewart would have to admit an infinitude of anti-REM structures. But then it would seem that if they're all real, you could kind of collect them all together and say that was a maximal structure. And that would be a violation of this extendability idea. You need the modality to get true extendability. And so that would be one place where, from the point of view of mathematical practice, anti-REM structuralism is closer, much closer to real practice. And Resnick's science of mathematics as science of patterns is also closer. But if you're talking about philosophical and foundational issues, I think the modal is helpful, very helpful. So maybe we should have both side by side doing different work. There's something to be said for that. There's another problem I have, though, with this Platonist view. And this is something that goes back to a famous paper by Paul Benasareff, who was professor of philosophy at Princeton for many years. He wrote some inspirational papers that got very famous. And one of them was, I'm trying to remember the title of Paul Benasareff's famous paper where he compared the numbers, the ordinal numbers according to Zermelo and then according to von Neumann. And there are different series of sets.
Is it the What Numbers Cannot Be paper?
What
that one?
Numbers Cannot Be. Beautiful title.
Yeah.
And he said, look, we have two ways of modeling numbers with sets. We have infinitely many actually, but here are two, and they're different. That was all he needed. So he said, look, there's the Zermelo way, which is you start with a null set, then you take the singleton of what you had just before to get the next number. So you just keep taking singletons. Just means putting another set of brackets around what you had before. So that's one series. But then there's this other series that von Neumann came up with, which proves better and more convenient in certain ways. You start with the same thing in the empty set, and then you take the set of all predecessors as your successor relation. Well, so the first non-empty number is going to be singleton empty. That agrees with the Zermelo. So Zermelo and von Neumann numbers are the same for 0 and 1. But what about 2? For Zermelo, it's just the singleton of 1, which is the singleton of empty. So it's singleton, empty. For von Neumann, his successor relation is to take the set of all the predecessors. And so you're going to have the set of the empty set and 1, that is the singleton empty, and you're going to have the set of that, which has 2 things in it. So the advantage of von Neumann's method is that the cardinality of the sets goes up as you move along. As you get more and more along the further, it makes sense that the number should be bigger, has more things in it. Whereas for Zermelo, there's always just one thing that's a member. But of course, there's a member of a member, and a member of a member, and so on. And so you keep track of it by iterating the membership relation. So he said, look, there's no way of saying the numbers are really Zermelo numbers or they're really von Neumann numbers. It makes no sense to say, but if those are the only two options, you have to say which, because there's only one natural number structure, right? There's the one we all learn in grade school, 0. Well, they don't talk about 0. You start with 1, 2, 3, so on. The counting numbers. So the first inference then from Benasareff's paper is numbers can't really be sets. Because if they were sets, we'd have to say, well, which sets are they? And they have to be unique. But we just showed with the Sermelo and von Neumann examples that there's no basis for claiming uniqueness. So the natural numbers, you couldn't talk about the natural number structure. So then you'd be back talking about multiple structures. And so it gets messy. And so he says numbers can't be sets. Not really. Well, what can they be? And then he says, well, you couldn't even say that they're objects because they'd have to be some particular objects. But you could get some other sequence. Even if those were all the objects in the universe, you could get a different sequence by just interchanging two of them. Take any two and switch them. Well, their order is different. So one is playing the number 2 in one structure and it's playing the number 17 in another structure. And so they're not the same sequence. And so you're back to 2 instead of 1. And there's no way to choose between them. They could be indistinguishable particles in quantum mechanics. So Benacerraf's paper seems to show that numbers are not objects at all. That also inspired my structuralism. And it tells against the anti-REM structurals. So one of the problems I have with the anti-REM structurals is that it seems to be subject to this permutation argument. So take Stewart's favorite anti-REM structure for the naturals and switch 2 and 3. It's a different structure because the successor of 1 is 2 in one and 3 in the other. Well, how do we distinguish between these? If 3 were red and 2 were blue, well, then we could say, look, 2 is by definition, the successor of 1 has to be blue. It would be arbitrary, but all right, it has to be blue. But at least we know what we're talking about. It's open whether 3 is red or not. So maybe the red one could be 3. But obviously, these idealized objects that are supposed to be abstractions, well, they're abstract. They're not in space-time. They certainly aren't colored. They can't be blue or green or yellow. So that makes no sense. So there's nothing that distinguishes them except their positions. And Stewart says this. He says they're identified as positions. They are just pure positions. Well, and so if they're objects, though, you could talk about a sequence where they're reversed, just like Benacerraf. So my question to Stewart is, why aren't your anti-REM numbers subject to the Benacerraf argument? Just via permutation, even if you don't even have to go outside the structure. Well, I raised that argument in print. I don't think I ever got a satisfactory answer, but that's one of the problems I have with the Platonist versions of structuralism. It seems that they're subject to something like the Benacerraf argument, if not directly the Benacerraf argument, that you've got these objects, you've got multiplicity. The problem is not the existence anymore, it's the uniqueness. You're supposed to be talking about a single structure, and really there are infinitely many. So that's my main problem with the Platonist version. But there's another approach to foundations of mathematics that's closely related to the modal that is worth mentioning. I don't know if we have time to discuss it, but that's called fictionalism. And it's the easiest way of being a nominalist. And I plead guilty to having strong nominalist inclinations. I'm tempted by nominalism and fictionalism. One thing I like about the modal mathematics that I helped develop is that one can be a nominalist as long as one is willing to talk about the possibilities of objects of whatever type you like, as long as you don't contradict yourself. It allows me to say, look, the only things real are what can occur in space-time, in our actual space-time. There may be other space-times. Maybe we have to recognize a multiverse in the physical sense. Well, if that ever makes sense, if we can think of universes as kind of islands in some larger space, maybe that would still be allowable for a nominalist. I'm kind of undecided about that. But I'm happy if we just have a single universe, even if it had a beginning, and even if it has an end. That's too bad. It's a very unpleasant business. But as one of Fred Hoyle, is held out for the steady state theory, in which the universe never had a beginning and it will never have an end. It's just always been around. Then the Big Bang theory comes along, and it's an insult to this Hoyle universe, a classical universe. General relativity holds, so it's not classical gravitation, but it's classically conceived in that it goes on forever and it never had a beginning. So there's no need for any explanation of how the universe began, because it didn't begin. It was always there. Well, the evidence for a Big Bang got stronger and stronger after the discovery of this background radiation by Penzance and one other co-worker in the late 1950s. They were looking for something else entirely, I think some kind of radio frequencies, but they found this steady kind of very, very slight hum everywhere in the background. And that was this leftover radiation from the Big Bang. There's a lot of evidence in favor of that. And so Hoyle's students started leaving the fold, giving up and joining the Big Bang cosmologists. And one of the important ones, Narlikar, was quoted as saying, so the steady state theory satisfies what's called the perfect cosmological principle. In terms of space, everything looks pretty much the same from any vantage point. That's the cosmological principle. The universe, if you're in the large scale structure of the universe, it doesn't matter where you are, it looks pretty much the same. That's the cosmological principle. The perfect cosmological principle adds, and whenever you look at the universe, it looks pretty much the same. So it's that perfection that fits with, an all perfect being. Temporal as well as spatial homogeneity. And that's what has to be given up if you buy into the Big Bang cosmology. So Narlikar said, the fact is, the universe is not perfect, and that we just have to recognize it's a botched job. There's a great cartoon. Can I take the time to give a great cartoon? It has 7 frames.
Sure.
So it's looking at God. It's looking at the creation. And there's no picture at all. It's just blank space, the frame 1. That's at time 0. That's day 1. And God says, there's plenty of time. That's what you read as the caption. You don't see God, by the way. God isn't a physical being. God is just God. And you're seeing its blank thing. Day 2, similar, completely blank. And God is resting and God is saying, yeah, there's still plenty of time. And this goes on till day 4. Things are getting a little questionable here. What's going to happen? Well, finally, I forget whether it's on day 5 or day 6, God gets busy. Maybe it's over a 48-hour period. And he's going berserk. And things are flying everywhere in every direction of space. And things are colliding into each other. It's brilliant cartooning. Day 7, the day of rest. Shows a couch with an old man in it with a beard, drinking a beer and watching a football game on TV. That's Shabbat. It's either Saturday or Sunday. I didn't commit us, but I love that. So the universe is a botched job. That's what Narlicker said, and we just have to learn to get used to it.
Good. Yeah. Okay. So building off of that, I mean, can you talk a bit more about the view that you've developed and, how you think that's an improvement or can help out some of the people who have come before writing on these topics?
Sure. Modal, the project I worked on and started developing is called modal structuralism, or modal structural interpretations of mathematical theories. That's a more accurate title, but it's too long for everyday use. But the idea is to get at mathematics conceived as a study of structures independently of the objects making up the structures. It's rather the organization of objects, the interrelations among objects that matters for mathematics. It's helpful to distinguish between pure and applied mathematics. Here we're talking about pure mathematics. Applied mathematics is another closely related concern, and it's addressed in this modal structural program. But first, let's think of pure mathematics and start with the most basic kinds of structure. So the structure for the natural numbers. Everybody's familiar with counting. You start with an initial number, whether you call it 0 or 1 doesn't really matter. And then each number has a next number called the successor of the given number. So the successor of 0 is 1, the successor of 1 is 2, and so on. Different numbers always have different successors. You never have one number, you never have two numbers having the same successor. Two different numbers always have different successors. And so the next thing is that the numbers go on and on. How do you say that? You want to say, well, there's no finite limit to how far the numbers go or can be taken in principle. Of course, nobody lives long enough to go through all the numbers. There are infinitely many of them. So we have this idea that of the infinite already with the natural numbers. So the standard view of a theory like this is says that, well, there are just these numbers are names, and they're names of objects. And so there must be infinitely many objects already they can't be identified with things in space and time because, there's no reference to space or time. The idea is that the numbers would be just as valid no matter what existed in the material world. And maybe everything in the material world is finite, whereas there are infinitely many numbers. So they're thought of as abstract objects, but abstract objects raise deep philosophical problems. They're not in space and time, and they don't enter into causal relations. So how can we ever know about them? What is it that enables us to state things in terms of numbers and know that our numbers behave in the right way? So we can assert truths and we can reject falsehoods, but we can't interact with numbers per se. What if there are no numbers? That shouldn't change the mathematical facts. Even if there were no abstract numbers 2 plus 2, 3, and 5, it would still be true that 2 plus 3 equals 5. So there's this idea this traditional Platonist picture thinks that there's just a world of abstract objects, even if we can't interact with them. And somehow we can know that certain things are true about those numbers and other things are not. It's quite a mystery how that's possible if we can't even interact or learn about these numbers as objects. So there's motivation for looking for another perspective. And the modal view says, so modal structural view is one that is both modal and structuralist. The structuralist part comes from just the interest in pure mathematics and studying different kinds of organizations of objects. So in the case of the natural numbers, it's a countable sequence, and it's discrete, 1, 2, 3, 4, and so on. But then there's this modal part, which says even if there aren't any objects satisfying the axioms that we've laid down for, say, the natural numbers, it's sufficient if there could be such objects. So there's this claim of possibility. It's logically possible that there be objects that are organized in this sequential way, with an initial starting point, no end point, and it's a discrete linear ordering, nothing in between two adjacent objects. Every object has its own successor, unique successor. And then there's the very important principle of what's called mathematical induction. It would be better named numbers induction, but it's always been known as mathematical induction. And that is for a property P to be shown to hold of all the natural numbers, it suffices to show that it holds of the initial one, call it 0, then we're talking about cardinals with Frege, and to show that if it holds of any given number n, then it also holds of n plus 1. If you can establish those two things, then it's legitimate to infer that P holds of all the numbers. That's the principle of mathematical induction. Now, if you if you state mathematical induction that way, the way I just did, you really have gone beyond the expressive reaches of what's called first order Peano arithmetic, because you've been talking about arbitrary classes or arbitrary properties. You say, for any class, if it holds of 0 and if it holds of the successor of anything that it holds of, then it holds of all the numbers, or every number is a member of it. So that's a way of reaching across this whole structure with a class that's properly organized. It's got the initial element and it's closed under this successor operation. But now we're talking about classes of natural numbers as well as the numbers themselves. And that's a much richer theory. That's called second order Dedekind Peano arithmetic. Now, the beauty of this theory is, though, as Dedekind proved in his great essay, Was sind und was sollen die Zahlen, which we mentioned last time, badly translated as the nature and meaning of numbers. As he proved, there are any two systems of objects that satisfy these conditions, including this induction principle. Any two of them are essentially copies of each other. There's a 1-1 correspondence preserving the ordering between any two such structures. So any two structures are said to be isomorphic. There's a function relating them, taking the initial one of one structure to the initial one of the other, and preserving the successor operation all the way up. And so they're mirror images or copies of one another. That's the famous isomorphism theorem. That's expressed by saying that the second order axioms of Dedekind are categorical. There's a unique structure that satisfies them. That's the ideal situation for the modal structural interpretation, because then we can generalize over any structures of this type that there might be. We don't have to say that there is any. All we need is that it be logically possible for there to be one, which is a much weaker statement than saying there actually exists such a thing. So this is the basic idea of the modality. We introduce this notion of logical possibility. And then we say structures of the appropriate type, such as one for Dedekind's axioms, are possible. And then we say that anything that we can prove about the natural numbers is true in all possible such structures. And there we use the necessity operator. We say necessarily T, where T is any theorem that we can derive from the axioms. So we have a very nice story, and we never actually have to say that there are these abstract individuals called numbers. All we have to say is that it's possible that there be enough objects arranged in the right way. And then we're off and running. And then what we achieve when we prove a theorem is a generality over any possible structure that meets the right conditions, that is, that satisfies the basic axioms. So axiomatic systems are seen as essentially definitions. They're telling us just what kind of structures this branch of mathematics is about. So that makes the theory of the numbers systems, like the naturals, the integers when you add the negative numbers, the rationals when you add all the fractions, and the reals when you take limits of sequences and you get uncountably many real objects continuously distributed, say, along as visualized by a straight line that goes infinitely far in the positive and the negative directions. And once you have the real numbers, you can get the complex numbers. That's enough mathematics to do just about anything done in the natural sciences, including physics, of course. So once you have the real numbers, you can get just about anything. By the way, the question, how many real numbers are there, is still completely unanswered. And we know that from the standard axioms of set theory, it cannot be answered. We need new axioms to decide it. And no one has come up with an axiom that the entire community of set theorists and professional mathematicians is willing to accept, is ready to accept. So that's called the continuum problem. It arose as early as set theory itself, which was back in the late 19th century by the work of the great mathematician Georg Cantor. And although he didn't come up with a definitive axiom system, he had the insight to ask this question: how big is the continuum? How big is the real number system? And that's come to be known as the continuum problem. Due to results of Gödel and later Paul Cohen, we know that the continuum problem cannot be answered in any known axiomatic theory of sets, which is very surprising and troubling in a way. But we can be convinced that there is an answer. And we don't have to be Platonists to believe that. All we have to do is believe that it's possible that there be a continuum. That is, that there be enough objects so that they're organized like the points on a straight line. So there is the essence of modal structuralism in a nutshell. You postulate the possibility of a structure of the appropriate type, and then you take any sentence about, quote, the objects of that structure to be a generalization over any possible structures of the appropriate type. And it's very helpful if you can show that the theory that you're working in is categorical. That's true, say, for the natural numbers. It's true for the integers, the rationals. It's also true for the real numbers. If you use the second order machinery, in the case of the reals, it's not the induction principle that's for natural numbers. Rather, it is for the what's called the axiom of continuity, the least upper bound principle. That is that every bounded set of real numbers has a least upper bound or a greatest lower bound. And here we're talking about sets of real numbers. So that's, again, the second order idea. If your first order objects are the real numbers, like the points on a line, the second order objects are going to be classes and relations of those points. And that's what we need to get a categorical theory. And that's particularly convenient because then any theorem corresponds to, so the modal structural interpretation of a theorem, say of analysis, which is a theorem about the real numbers, turns out to be, so it's translated into, for any structure that looks like the straight line. That's by infinite. It's infinite to the left and to the right. For any structure of that type, the sentence in question holds within that structure. It's shown how to translate. This was in my book, Mathematics Without Numbers. How to translate a sentence like that into the language of pure structure theory. Now, another comment. Since we have the modality, we only need to assert the possibility of structures of the right type. We don't say that they really exist. Maybe they do, maybe they don't. Maybe they can be found in nature, maybe they can't. A lot of finite structures can be found in nature. But then it also depends on your theory of nature. Is there such a thing as space, empty space, or empty space-time? And if so, what's its structure? Does it have uncountably many points in it? What's a point, right? There are those questions. We don't need to say anything about the physical world to go as far as we want with pure mathematics. We can stay neutral on the question of the nature of space and time. What we want to do, though, is provide for enough mathematical structures so that any science like physics can just take something off the bookshelf from the mathematics section and use it however they find it useful or however they see fit. And we claim to be able to do that with this modal structural interpretation without ever making any commitment to the actual existence of infinite structures. It's sufficient if they're logically possible. And then we have to tell a story about how those logical possibilities get applied to the natural world. But that's not too hard to do. And we can just imagine that we can just stipulate that if the natural world were embedded as a part of a structure of this type, so long as the purely mathematical machinery doesn't interfere in any way with the physical world, the material world, then we're fine. Then we can go about our applied mathematics in the usual way. And we're just stating relationships between these extra objects that carry the mathematical information and the physical. And those relations might be quite close or they might be quite far removed. It doesn't matter. All the machinery is there for the sciences to proceed. So that's the basic idea of modal structuralism. Get rid of commitments to actual objects. Just talk about logical possibilities and do it carefully so that you keep your you keep your mathematical language as free as possible from a reference to actual objects. All you need is that there be the logical possibility of enough objects suitably interrelated. And it's that suitably interrelated that does the work.
Very, very good. Okay, so yeah, so many things I want to cover here. Maybe we'll only get to a few of them, but the first thing is at the end there, you're sort of saying that it's almost like you're making a suggestion like about how to use mathematical language. We can understand it in this way, and here's how you get mathematical truths, as long as there's these possibilities and so on, without having to commit to mathematical objects or structures of the relevant sort of the actual world. But it could be that people are mathematicians, scientists, or people generally already are committing to these things. It sounds like, is this right? I mean, you're just making a suggestion, like about how to,
Yeah.
Right? Just to do without those.
Yeah, it's a way of seeing mathematics so that you don't have to be committed to actual carriers of mathematical information. Now, you may have enough things around in your ontology. Maybe you believe in space-time points, for example. Well, presumably then you believe in a continuum of maybe a four-dimensional continuum, three spatial and one temporal dimensions, and you've got enough objects there to carry all the mathematics. But what the modal structuralist adds here is that you don't have to believe that. You don't have to be a realist about space-time points in order to make sense of applying mathematics to the material world, or just looking at mathematics in abstraction from any such applications. It's not necessary that you have actual carriers of the structural information. So it's a way of freeing mathematics in a way of ontological commitments. You may make the ontological commitments if you want, but you don't have to. So it's compatible with a kind of nominalist view of the world, which is that the only things that we really have to take seriously in our ontology are things that enter into causal relationships with other things. And the causal relations can be very, very strange, as in quantum mechanics. It could be that there are properties that don't make any sense except under the right conditions, and that, well, there are unsolved theoretical problems in quantum mechanics. Modal structuralism doesn't help at all solving those. But at least you don't have the added worry that there might not be enough objects to carry the mathematics. So the nominalist view is that ontology can stop with the physical, the contents of space and time, the actual contents. Now, we don't know what the large-scale structure of space and time actually is. We don't know if there's going to be expansion going on into the infinite future, or whether it seems the case now that it seems that the things are moving away from one another too fast and too far to ever fall back by gravity. Or it could be that there is enough matter and energy in the universe so that it will fall back and eventually contract to a very, very small, dense, hot fireball. And we don't know what happens then. Is there going to be another Big Bang, sending things outward again, or is it going to collapse literally into a black hole and vanish effectively? We don't know the answer to those questions, but in any case, we can do the mathematics of whatever the scientists give us without going beyond their ontology with the mathematics. So it's a kind of, we give up mathematical ontology and instead talk about the possibilities of structures of the appropriate sort.
Good. Okay. So one thing you mentioned there was that, yeah, this is compatible at least with the nominalist picture of the world. There's maybe just the physical world and stuff going on there, and there's no sort of abstract objects apart from that or anything else, perhaps.
Right.
But I was wondering, like, one motivation someone might push in favor of Platonist view. I mean, even if they grant to you that, well, okay, we could understand mathematics in this way, there's arguments to be made that we can't understand various other things in analogous ways. For example, maybe we have good reason to posit abstract objects to account for things like propositions or properties, relations, universals, possibilities, fictional entities, other things like that. Maybe that's most of the list. Maybe, and the idea is maybe that, okay, if we buy into abstract objects in these domains, I mean, why not buy into them in the case of mathematics? It's just fill out this abstract realm, Platonist realm. I mean, what do you think about maybe this sort of argument and
yes,
the abstract views about those other things?
Well, it is a serious argument, and nominalists, yes, it's a serious issue that's raised there. Maybe there are other areas in our ordinary conception of things and our ordinary language where we're committed to abstract objects, such as, letters of the alphabet, right? We distinguish between letters of the alphabet, A, B, C, D, and so on, and inscriptions thereof, or utterances thereof, right? What's a letter? Well, it's a shape of a certain form. What's a shape? Well, the nominalist, a thoroughgoing nominalist, has to tell a story about all of that. And there have been efforts in those directions, and it's questionable whether they are entirely any of them is entirely successful. So I would grant that that's part of a nominalist program. It's a work in progress, and it's not entirely completed, I don't think. Now, there have been stabs at it. So, for example, and also there's motivation for it. I mean, take something like, take an institution like the U.S. Postal Service, right? It's an institution. It's literally a social construction. But what kind of an object is it? Is it located just where all of the postal stations are? Or do we need to talk about it as an object at all? Maybe we can say everything we need to say. In other words, we can talk about certain patterns of human behavior and interactions and consequences of actions, implications of actions, and so on. So a whole network of actual behaviors. Maybe you could use modality here too, potential behaviors. We can talk, or conditional things. So if somebody puts a stamp of the right kind on a letter and drops it in the right place, in the right kind of box, then it is reasonable to expect that the recipient, the intended recipient of this mailing, will actually receive an envelope with this stuff in it, right? So there you kind of reduced the talk of the post office or the postal service to human interactions, expectations, and patterns of behavior. It would be very complicated to make this all explicit. But I think that one could say enough that it seems not unreasonable to think that in principle, we could get by with this much more long-winded talk of human expectations and interactions on a social level. And if we can talk about expectations and behaviors, maybe we don't need to really take too seriously quantifying over things like the post office, or the postal service, the postal. So that's a way of approaching talk of social institutions in terms of human interactions and expectations. And then one could do the same thing on the biological level. Well, what are humans? Well, we are, chunks of matter and energy organized in special ways. And maybe it all could be talked about in an idealized language of physics, where we could talk about wholes made up of physical parts that are organized in the right way, so as to be capable of various kinds of behavior. And all of that could be given physical descriptions. Well, that's a physicalist conception of animals, including humans. Whether it can be fully successful is still a subject of debate because of not so much the physical, but the mental. Maybe we can come to talk about human bodies in purely physical terms. Although that would be quite a challenge too, because we have all kinds of functional language. We talk about the function of the heart to pump blood, the circulation of blood and all the things that it carries. But it's another thing to talk about, to avoid talking about the human brain and the human mind, or talk about the human mind or human mental interactions with a community of minds. To do that all in physical terms is a daunting project. So we don't have to decide those things, but as far as mathematics is concerned, I think a good case can be made that we don't really need to talk about mathematical objects in a serious way. It's sufficient to talk about the possibilities of organizing enough things in the right ways. And we can get by with that. So in this sense, mathematics is a lot simpler than those questions I was raising about on the level of human interactions and social institutions. That gets a lot more complicated.
Right. Yeah, for sure. But yeah, I can see how that's kind of start there anyway. So another worry that someone might have for your approach is that, of course, a lot of this is stated in terms of logical possibilities. And, well, I mean, someone might worry that you're just maybe pushing the problem back a level. So you might think, okay, maybe we don't need to suppose that there are these mathematical objects, but what about these possibilities? How do you get logical truths and logical possibilities without abstract objects? And I think, I mean, you've said that on your view, we can have these possibilities without any like real possible worlds or possibility of any sort. But like, how does that work? I mean, do you have a view about sort of logical truths, logical possibilities that don't require those things? Yeah,
Sure. So we can point to the fact that the use of these operators. So it's possible that there are countably infinitely many objects arranged in a series, like the natural numbers, 1, 2, 3, 4, and so on. That's a possibility that there be such objects. That is very different from saying that I'm committed to, quote, possible objects. There's a possible 1, a possible 2, a possible 3, and so forth. I'm not even sure what that really means. But by saying that such a structure is possible, I don't have to be accepting anything actual or anything real answering to the possibility. I don't have to be accepting a possible world with objects like that. That would be another move. That's kind of Platonizing the talk of the modal talk. We have to claim, rather than it makes sense to just say there might be enough objects arranged in this sequential way, like the natural numbers. There might be, without saying that there are possible objects that are organized this way. That's a manner of speaking, but we don't have to take it seriously, because we can everything we can do with that, we can do with just saying possibly there is a series of objects. We don't have to interact with, we don't have a problem of interacting with the elements of that series, because they don't enter into a causal physical reality, and they don't enter into any reality. They don't exist. All we're saying is it's possible that there be. And then we use neutral language, that there be objects of whatever sort that are organized in a certain way. So you can say we're talking about patterns, but even that you can't take literally. It's not like there's something out there that's called the pattern of natural numbers, and our mind is latching onto it. That's all colorful talk, but we don't have to take it seriously. We can just write out. We can just say there might be, or there could be, or there could have been, or it's logically possible that there be. And that should suffice. So if we can understand these locutions without the ontological baggage, then that's all that the modal structuralist needs. So I think the challenge for somebody who insists on abstract objects is to say that there's something that cannot be said that needs to be said for the sake of some scientific program that requires these abstract objects. And let's see if that's really the case, because I don't think it is. It's certainly convenient. I mean, if you want to talk about human institutions like the post office, it's very convenient to have this language of referring to, social governmental institutions and so on. But the nominalist would need to say that, let's first try to eliminate reference to institutions like the post office, conceive it just as a shorthand for the way individual humans are capable of interacting And the expectations and interrelations that they have that bear on this this institution, and see if we can say everything we want to say in terms of the individuals, their expectations, and their interactions. And we also are allowed to use counterfactuals. If I take an envelope with a proper stamp on it and put it in a certain box, right? If I were to do that, then I could reasonably expect that ... Eventually, that piece of paper with a stamp on it would wind up in somebody's mailbox, right? So there would be a whole lot of counterfactuals like that you'd have to evaluate. That would be associated with, a simple statement of, the way the postal system works, without actually quantifying over anything that counts as the post office. It's rather, that's shorthand for all these reasonable expectations that people have for doing this or doing that. So that's just a start and a suggestion for how to proceed. But you're quite right that it's a tall order for the nominalist to say everything that needs to be said in those terms.
Right. Yeah. So regarding logical possibilities, then again, I mean, I get the point where you can say maybe we can have these logical possibilities, or it could be logically possible that blah blah blah, without having to be a thing that is a logical possibility, or like a possible world, or like a possible object, or something like that. Mm-hmm. But like, I mean, I guess I could see someone having two remaining worries, right? One is, well, the logical truth itself, we might think has to be a proposition, and so maybe that has to exist in an abstract object. And two, how is it that it's true? I mean, maybe do you have a more full account of how you get truths of this sort without like possible objects or possible worlds in any robust sense? I don't know. If you want.
Well, that would be like giving a semantics for modal,
right?
Modal language, and the semantics might avail itself of apparent reference to abstract things. You'd have to have a method of handling that or translating that into further nominalistically acceptable idiom. So, it looks like there's this back and forth, this kind of hierarchy. It's certainly convenient to talk about possibilities as though they were actual things you could grasp, but the idea is not to have to do that. It's just a convenience, a way of speaking, a manner of speaking, to talk about, to reify possibilities. So let's see. There might be, let's take the case of the natural numbers. So it's logically possible that there be a sequence of things arranged in the usual way, 1, 2, 3, 4. So now you worry that at some stage we're going to need to talk about. Now, see, what was your example of something that wasn't going to be, that was still a problem for the nominalist? What was your example?
Yeah, so one would be that you might think that logical truths require the existence of logical propositions, which are maybe in abstract objects.
Yeah.
And then, maybe the truth of those logical truths requires abstract objects of a certain sort.
Right. So, well, it would depend on what work propositions are supposed to be doing. But the natural nominalist approach there would be to eliminate reference to proposition using modal language in connection with sentences or bits of actual languages or manifestations thereof, speech patterns, patterns of inscriptions, and so on, and how people or other intelligent creatures interact with those things. So it would be a complicated story for sure. But in principle, I don't see why it should be regarded as undoable. It just be so. In other words, talk of these types, like linguistic types, predicates, sentences, paragraphs, and so forth. All of that is very convenient, but it's all constituted of actual events or events that could take place under the right conditions. So I would think, especially if you are allowed to use modalities, that a convincing case could be made that one could get by without that ontology. But it is a tall order. I'll grant you it's a tall order and maybe much messier than getting rid of abstract mathematical objects like numbers or sets even. Because here you're talking about properties and relationships of interacting complex objects themselves like human beings. It could get very messy. But the same idea would be that the apparent need for a Platonist ontology comes about because of convenient ways of talking. And that in principle, those convenient ways of talking could be replaced or eliminated with much more complicated, ontologically rarefied substitutes. But I agree, it's a tall order for the novelist to actually come up with such substitutes. But the idea would be, this is a convenient way to talk, but it's not really necessary. So it's very convenient to talk about institutions like the post office. Much more complicated to talk about all of the different human interactions that go along with there being such an institution. So the modal structuralist is not going to have a satisfying solution to all these different problems, but maybe it can be pointing in a useful direction. I mean, pure mathematics, by comparison, is much less messy, in spite of the fact that it's up to its neck in the infinite. In a way, it's easier to approach because you have so much work has already been done organizing the subject, right? You've got it broken down into all these different types of structures. You've got all these different systems of axioms. Think of all the different algebraic axiom systems there are. And so the mathematicians have done a great deal of work for us by organizing their field. But when you get to biology and, the social sciences, things are much, much more complicated and messy, even though they're almost presumably dealing with the finite. So I agree, there's a big project there. And all I can say is that modal structuralist approach makes a start, at least with pure and applied mathematics. We haven't talked much about applied mathematics, but one can see how that goes pretty well, and that's still, in a way, much simpler than the kind of area that you're talking about, where you have to actually deal with things like institutions and social organizations and so forth.
Yeah, I was also thinking, maybe the modal structuralist view could be, perfectly fine, even if it turns out that we have to be committed to these other sorts of abstract objects or something else like that. Even if it turns out that we couldn't do without it, okay, no worse. Modal structuralism is no worse off. And if we can do without them, great. Yeah.
Yes. Right. So this, this is a program for future work. How far can this modal structural approach be taken to make sense of other areas of human inquiry that are important to us? And in some of them, maybe it can, and others, maybe not. One place where there might be some very interesting work to be done is in the area of economics, which is supposed to be the most natural scientific of the social sciences, right? Mathematics is used in sophisticated ways. You have the phenomenon of building simplified models of complex human behavior. It seems that you're dealing with structures a lot. The organization of an economy, there's a lot of idealization that goes on, some of it better than others, some of it more scientifically helpful than others. It would be a good area to start if you were going to try to see how modal structural ideas could be useful or might not be in making sense of the applications of mathematics in an area like economic systems, where the mathematical work is already pretty advanced. So this would be an area of applied mathematics, but it would also be a challenge to, the philosophy of the social sciences. To what extent do we run into problems similar to the debate between nominalists and Platonists? To what extent do we need to take talk of properties and relations seriously in terms of their ontological import, as opposed to just convenient ways of speaking? That's a challenging area for future work.
Yeah, fair enough. I don't know if you want to add anything more on that, but so I did want to talk about, so you've sort of been talking about this a bit already, but when it comes to science and indispensability arguments, I take it that I'll give a brief overview of indispensability arguments in a second, but like your suggestion is the way to do science without numbers is by doing mathematics without numbers, right? I mean, that's kind of the whole point. And okay, so for the audience, the basic structure of this kind of indispensability arguments, at least like the Quine-Putnam version, well, there's more to it about, Quine's stuff about ontological commitment and so on. But the thought is that, like, okay, we should be ontologically committed to the entities, the commitment to which is indispensable to our best scientific theories. If our best physical theories, quantify over numbers, they involve commitment to numbers, then we should think that there are numbers. And then the second premise is that our best scientific theories do involve the sort of indispensable commitment to those things. And so, we should be committed to those things. And I take it that your response to that, mobilizing your modal structuralist view is that, no, they are dispensable because we can replace the mathematical talk with this modal structuralist mathematical talk, which doesn't involve that ontological commitment. Do I have that right? I mean, is that?
Yes, I think so. I think that's exactly the line of argument that can be carried out. So if you take, let's say go back to classical physics. So classical physics often deals with idealized models anyway. So you're talking about, some finite distribution of point particles. And maybe you'll specify some forces acting between them. This is already different from the real world because point masses don't exist as far as we know. It's a mathematical convenience, but we can talk about point masses and we can apply physical theories to systems of point masses, and we can find out how the parts of these systems interact and how they behave over time. And now, the modal structural ideas can be applied in this realm. You would need a separate application from what has already been done because you're talking now about something much closer to what's encountered in the physical world. You're talking about point masses that interact in certain specified ways in accordance with certain rules or laws. So there may be gravitational attractive forces between these, and you want to say how they behave over time. All of that could be spelled out in similar terms to the way the modal structuralist spells out the pure mathematical case. You could say, possibly there are these objects, which we call point masses. You can say what properties they have. And then you can specify that there are forces obeying certain rules that operate among these point masses. And then you can use mathematical methods to describe how the system evolves over time. Not over real time, but over time in this structure. Right? So you can be talking about a structure obeying certain equations over time, and then get a lot of useful results that way. And do you need to be committed to any abstract objects here? No, because you're just saying we're talking about the possibility of objects of a certain sort. Here, they're going to be point masses under behaving in certain ways as governed by certain forces obeying certain equations. All of that could be stated in nominalistically acceptable language. And then you are just talking about what would happen in such a system set up in a certain state at T0 and left to evolve according to these partial differential equations or whatever the laws are until time T. And what's the result going to look like there? And you give a description of it. So that's an outline, a way of applying some of these ideas to a physical situation. It's an idealized physical model you're talking about. And again, you don't have to be committed to the actuality of these point masses. You can just say, this is a possible structure. But we can learn things about actual physical systems by studying the mathematical behavior over time in the model, right, of these idealized objects evolving under the operation of just certain specified forces. And we'll ignore any other, we'll pretend it's an isolated system. Now we come to the real world and we have some real particles. Let's say they're a gas, but it's pretty well isolated from the rest of its environment. And so we can see if it evolves in accordance with the idealized model. And if we haven't idealized too far, maybe we get useful results. And physics kind of succeeds when we learn how to do this. And so that's the kind of story one could tell. So you don't have to really buy into the actual existence of point masses or these idealized physical forces, laws. So we're saying that these are the only forces operating on these thingies. That's an idealization. In the real world, there are other forces that are going to be acting. But when we go to apply this kind of a theory, the actual world that we look at, or part of the world that we look at, we can make judgments about if it's close enough to being like one of our idealized systems. Then we will expect the kind of evolution that our mathematics delivers. But of course, it won't be perfect. Well, it'll be highly imperfect. And it just depends on the setting, the context, how accurate your model has to be, right? If you're planning a manned space flight, you better be pretty darn accurate, right? Because human lives are going to be at stake. On the other hand, if it's only rats, well, maybe we can tolerate more error and so on. But you get the idea. So there are practical questions here about how close to the ideal model do we have to be for this application to be useful, application of mathematics to be useful. But that's a way to start, is to work with idealized models. And I think that's what the physical sciences do all the time, right? Now, maybe they need to talk about propensities in a way that brings in stuff that goes beyond the modal language. You're talking about properties here of a special kind, right? And now, are those abstract? I'm not sure. I think that one way to look at some of these problems is to think of properties in an Aristotelian way rather than Plato's way. For Plato, they're abstract. They're in the sky somewhere. There's something called humanhood or manhood or whatever, sisterhood. But Aristotle had this idea of properties occurring as inherent in individuals. So he talked about the whiteness in John, right? Or the tallness in Peter or whatever. And so if you think of properties that way, they're much closer to being individual characteristics. They're individual characteristics. And you can think of them as real as the individuals that possess them. So the particular color of the back of my right hand, it's kind of it's a mixture of pink and tan as I see it right now in front of me in this lighting. It's not white, but it's more pink and tan. You can think of that as inherent in my hand. So it's not anything abstract. It's a characteristic that we actually see. And the same with the feel. It feels a little bit smooth, but not very smooth. Not as smooth as the surface of my table and so on. So there's a smoothness or roughness, and it's highly individualized. It's just as much part of me as my fingers are part of my hand. So that's a different way of talking about properties there. And I think that can take us some distance anyway toward dealing with property talk. And then if you want to generalize on that, maybe you can get by saying, I'm talking about qualities that are sufficiently close to these that are actually instantiated. And I'm idealizing. And maybe counterfactuals come in to do some work there too. You can say, what if there were individual properties that were not actually manifested, but could be manifested? Then what? And then you could start developing a theory and applications of these individualized properties. So that's one step that can be taken in an area that, has often led to Platonistic conceptions. But I like this Aristotelian approach better, obviously. I think it's closer to the way scientists speak of properties, right? So I don't know how helpful that is, but it's a stab.
That is helpful, yeah. I did also want to, another thing about logical possibility, because I mean, someone could think that it's actually even too, this constraint is too strong, because you might think that there's some room for, or that we don't want to rule out sort of at the outset, like inconsistent mathematics. Like, what if there is? why not suppose that we can have a mathematical system which is not classically logically consistent, but if it has to have a logically possible, instantiation like this, then you don't get. I mean, see where I'm going with this. I mean, what do you think about?
Yeah. So, and now you're broaching a very interesting area of philosophy of mathematics called dialethism, like Graham Priest. I don't know if you interviewed Graham Priest on this.
Yeah, a while ago, yes, I have. Yeah. But JC Beale as well.
Right. And so there they tolerate contradictory statements. And so classically, they don't have any models, but they have means of kind of corralling these contradictions and keeping them from infecting the whole system by truncating the logic. They don't allow what they call ex falso quod libet, that from a contradiction anything follows. It should be ex contradictione quod libet, but that's too many syllables, so they say ex falso. It's really from a contradiction anything follows classically. That's true by the classical definition, because the classical definition of implication is that the consequent holds in any situation or in any structure in which the antecedent holds or the assumption holds. And if the assumption is contradictory, then there's no world or situation in which it holds. And therefore, of course, in every world in which it holds, whatever follows. Right. So the classical definition of implication is too broad, too easy to meet, according to the dialethists or the relevantists. You don't have to be a dialethist. The dialethist believes that contradictions, in a sense. In a sense, they accept them as true, but they say they're also false. So don't worry. It's not that they're simply true. They're true and false. The classicist makes no sense of that. It says you can't have anything that's both true and false. That's to misunderstand truth values. But the classicist and the dialethist talk past each other completely. They just don't have any common ground. Now, the dialethist isn't so troubled by that because they're used to contradictions. But the classicist can't tolerate it. And so the classicist is going to walk away from that conversation frustrated, shaking his or her head. The relevantist, on the other hand, is not a dialethist, right? The relevantist just says you don't have an implication from a contradiction to an arbitrary sentence. It's not that the contradiction can be true and false. It's that, contradictions are always just false. But we do not want a contradiction implying anything. There has to be a positive criterion met of relevance between the assumptions and the conclusion. So you can't go off talking about something on a different planet from where you started and really have a logical implication. So yes, there are these alternative ways to the classical. And now, what was your question originally? Because I think
Well, it was just that, what if we wanted to allow mathematical systems that were, non-classical or allowed for contradictions?
Right.
What would be
right? Yeah. We could be more tolerant of them, and we could rope them off, so to speak, using the machinery of a relevance logic. I don't see anything in principle wrong with that. It would change the way we talk about applications of mathematics, for sure. It wouldn't change how we're dealing with the pure mathematics, though, that I can see. Maybe we'd have to branch out and admit more kinds of structures that have some contradictory elements, but those contradictory elements don't infect the whole thing. They're kind of confined or corralled. It's like containing an outbreak of a contagious disease, keeping a population isolated. So putting the bad guys in jail until they're reformed, et cetera, et cetera. So you can think of analogies here, and some of that could be made to work perfectly well. So you'd be dealing with different background logic in your reasoning, even in developing these structuralist ideas. So yeah, for simplicity, we've been working with classical logic all along, but I don't see any obstacle in principle to taking your background or underlying logic to be a relevance logic. I'm not sure what would happen if it's dialethist. Then I'm not sure how one goes about telling a structuralist story. But I can certainly see that it might work pretty well with one of the relevance systems. That would be an interesting project for somebody to work out. See what would have to be changed in the story I've been telling if you substituted the background logic, instead of taking it to be classical, take it to be a relevance logic. You might get some interesting differences.
Right. Or something that could be more permissible. Because I was also thinking, like, what about, constructivists or intuitionists opposed to mathematics, and or generally, what if you reject or don't affirm anyway, exclude a middle?
Yeah. Yeah.
Because there might be independent reasons to reject that. People think sometimes about vagueness and so on, that
right.
Or specifically in mathematics.
Right. So that would be an interesting project too, just working with the non-classical logics that have been dominant in the foundations of mathematics. So you have various kinds of constructivism, the most radical being Brouwer intuitionist systems. The logic for that has been well worked out, and given their understanding of the logical symbols, according to what are called the BHK rules, the Brouwer-Haitink-Kolmogorov rules for the different logical symbols like and, or, and not. You see immediately that excluded middle is not something that anybody would want to affirm. I've written on this. I have a paper called Never Say Never on the communication problem between intuitionism and classicism. It's in my collection what's the title? The title of my collection, Mathematics and Its Logics. So that paper, Never Say Never, is in there. That was published at Cambridge University Press, 2021. So Brouwer, Haitink, Kolmogorov explain what they mean by and, or, not, and the quantifiers. If then. So everything stated not in terms of truth, but in terms of proof. So if you say P or Q with or meaning, or the intuitionistic connective, that means the way to get at that is Either we have a proof of P or we have a proof of Q. Now, suppose we have not. To say not P is we have a method of deriving a contradiction from the assumption that P. That's what not means. It is manifestly contradictory that P. We get a contradiction from the assumption P, then we can say not P. Now let's consider a classical law, P or not P. Well, according to the BHK, Bauer-Heiting Kolmogorov reading of that, it says either we have a proof that P, or we can derive a contradiction from P. Is that always true regardless of P? Well, surely not. There are many P's where we don't know, and we can't prove that it's contradictory. We can't prove it. So there obviously it would be, so that law of excluded middle is unacceptable to both parties. So you see here, we're making progress. It depends on what the symbols mean, whether you accept a law or not, because it's a different law. So the classicist agrees with the intuitionist. So there's not a disagreement over any logical law. What do they disagree on then? They disagree on whether the classical language is really meaningful. The classicist says, of course it is. We have this idea of objective truth or failure of objective truth. And the intuition says, we don't know what objective truth is. We understand just what it means to say constructively, 2 + 3 = 5, because we can take this 2 and we can take 3 steps in the number system. 3, 4, 5. There we go. There's 2 + 3 = 5. That's the sense we can make of any proposition. And then the classicist comes back and says, okay, but from that way of using language, we think you probably can't do justice to the natural sciences, especially physics. And that's where the debate gets really interesting. And I think it's pretty unresolved. I mean, the classicist then is conjecturing there is some important physics that you cannot do with your restricted logic, because you're asking the logic to claim more than it can. But then you're going to lose. If you do that, you're going to weaken your system. So you won't be able to do the work that classical logic does for physics. And even though it's an idealization, this way of doing logic gives you predictions that can actually be subject to empirical test. And you won't be able to derive all those predictions using your weaker logic. Anyway, so that's how that debate can be played out. And the jury is still out. I think I've found cases where it's very unlikely that the intuitionists can succeed with the mathematics that is needed. But as I say, I think the jury is still out, at least from their perspective. But the lesson is that you have to keep track of how the logic is being understood. if you don't, you miss out on where the disagreement actually lies. Right? So there's more agreement than you would expect between the constructivist and the classicist. Everybody accepts that constructive excluded middle is not a logical law. Classicist agrees with that because it asserts something different. It asserts either provability or refutability, and there are all these undecidable sentences that we can't do either with. So nobody wants that law. So you forge more agreement, actually, once you recognize that they're using different languages. They're speaking different languages, so you have to translate to get proper communication. So that's one thing I would say, that the classicist doesn't have a monopoly on logic. It's certainly an idealization, and it depends on the purpose of your applications of logic. Which logic is the more appropriate one. So I would be a logical pluralist. Seems to me the constructivist logic makes a lot of sense if you're trying to keep track of constructive content. What's provable from what. It's much more convenient to work with the intuitionist logic than it is classical, because you've kind of built into the intuitionist idea of implication that there is a real common content being preserved when you make an inference. And you can't just go from, well, they accept ex falso quod libet. Intuitionistically, if you could prove a contradiction, you could prove anything. But you could combine intuitionist logic with relevance logic, and now you've got more restricted logic. That's what Neil Tennant, my good colleague down at Ohio State, calls core logic. He says core logic should be constructive, that is, following intuitionistic constraints, but it should also be relevantist, requiring that there be a connection in content between assumptions and conclusion. And that's really the most acceptable logic. And it'll be interesting to see how far you could develop mathematics starting from core logic. Just what part of classical mathematics could you recover? I don't know the answer to that. I haven't studied it. But Neil Tennant, it would be the person to interview on that. It'd be very interesting. Have you had him on this?
No, I haven't. But it sounds interesting.
It's something to consider. And he might have quite a bit to say about that question, because that strikes me as a very interesting topic for future research. How far can you get in terms of scientific applications with this combination of restrictions? So it's more restricted than constructivist or relevantist on their own, because you're combining the two kinds of constraints. And there's good motivation for doing it, for doing core logic. I'm just not sure where it breaks down, where it's just not powerful enough to get you what you really want or need, say in the science of quantum physics or something like that.
I was just going to mention as an aside that core logic approach is sort of reminiscent of what when I talked with J.C. Beale, he is a proponent of what's called first degree entailment sort of logical system, and somewhat similar, although it's not technically constructivist. But what he said about mathematics is that, well, yeah, maybe you can't get all the sort of mathematical results you want just starting with this logic. But like in other areas, mathematical theories might satisfy or validate more consequence relations than the strictly logical ones. So you can have a classical mathematical system. It's just that your things that your axioms, so to speak, will include, well, certain what you might call classical logical principles. They're not strictly speaking logical truths, right? But they're true on that theory or something like that. And so you can have
you have a stronger requirement to be a mathematical truth than just following classically from the axioms. You need to follow in the right way, and that's kept track of by some more rules or restrictions. And that could be very useful. And the way I've understood this question, you could actually build this into your computing machines, that these extra precautions need to be taken before drawing an inference, so that, and if something went wrong and you got a contradiction, you would have ways of isolating it, because you could show that without the full strength of your system, you could still get what you want. That would be the strategy. And so even though you're looked at classically, these assumptions lead to a contradiction. But if we look at it from the relevantist perspective, we can kind of shield ourselves from the bad stuff. It's like weeding out the bad apples. And that could be very useful. You could have, and I'm not up on this, but I would think that there are some computer scientists out there that might know the answer, whether, relevance logic has been actually implemented in any of the programming that's been done on, automated problem solving and stuff like that.
Right. That's a good question.
Yeah, so Neil might be a good person to have on some of these interesting topics, because he specialized in these weaker logics.
Right. Okay. Yeah. I'll be sure to send him a note to see if he's interested. Yeah. So I normally end these interviews with more metaphilosophical question. So what do you think is the value of philosophy? Maybe in particular, like the philosophy of mathematics. Like, why do you find it worth doing? Like, what's kind of good that comes out of it? That sort of thing. What do you think?
Right.
Tough question. But.
You want me to try to say something about that?
Yeah, I mean, I know it's a broad, difficult question, but
in closing, well, there's always the answer that this stuff is fascinating, this stuff is interesting, and it's great to be able to delve into it. But I think it's also very useful to stand back and have perspective on a field that has gotten so far as our best scientific fields. It gives you an appreciation of the kind of questions that arise when you ask, what are the starting points for this great subject? What are the basic assumptions? And how reliable are they? What can we know about them? We want our system to be very rich. We want it to be very powerful. On the other hand, we don't want it to be so powerful that it can prove contradictions, unless we know how to isolate them, and then maybe we can let it be more powerful. But that's this issue about relevance. But just starting off and asking, well, why pursue something like philosophy of mathematics or philosophy of physics or philosophy of science, whatever, philosophy of the social sciences? Well, better understanding of the sciences themselves is one major motivation. Of course, there's no substitute for studying the science, but the textbooks may presuppose stuff that raises questions and that need to be addressed and that they don't address. You have to start somewhere. And so, for example, any good physics text is just going to assume a whole lot of mathematics. And they're not going to ask questions like, what are these mathematical assumptions rest on? They're just going to go ahead and use whatever is convenient to use. So somebody has to ask about the starting points. Now, what about mathematics itself? Well, you find these different axiom systems. Some are generally accepted, but still, it can be useful to ask, do you really need these assumptions? There are some strong claims about the infinite here. Do we really need all of that? That's one question. And if you do, well, how do you know that your system isn't going to lead you to a contradiction somewhere? Gödel showed that you cannot prove the consistency of such a system by within the means of the system itself. That is, if the system is strong enough to do arithmetic, you cannot prove the statement of the system's own consistency. Well, that's unfortunate, but what are the best substitutes? How close can we come? And if we can't do it by a mathematical, logical argument, then what kind of evidence can we have that our mathematical system is still good enough? It's fine if, we can live without certainty. We don't have to have a proof of consistency. Can we have at least good reasons to believe that our system is a good one? Meaning, including the implication that it's consistent. And there's no Gödel theorem blocking the way. We can get good non-mathematical reasons. That is, we've tried using the system in this wide variety of contexts. Say the rules for the calculus. We've done it in physics, we've done it in chemistry, we're doing it in economics, et cetera, et cetera. And we've gotten these great results. Well, that tells us something. At least if there's any problem, it hasn't arisen so far, and it hasn't blocked the way. And then the results that we've gotten have been very useful. We've built on those. And so we have kind of indirect kind of confirmation from the success of applications that our starting points are legit. So we can get evidence, even though it's not certainty. It's not as good as having a consistency proof of the sort that Hilbert wanted. And Gödel showed that, you've got to lower your sights. So that's exactly what I'm doing. I'm saying, let's take Gödel's advice. Let's lower our sights and see if we can achieve something, like second best, even though we can't achieve first best. We don't have to throw up our hands and give up the game, so to speak. So there's great value in exploring, what's the next best? And can we achieve that? Right. So we're dealing with some kind of weaker justification than knock down mathematical logical proof. That's asking too much. We can't get consistency proof that way, but we could get evidence, strong evidence, for our systems being contradiction free. So that's part of the approach, I would say, is to be more practical, to lower one's sights, and to acknowledge that, our knowledge is just not as perfect as we'd like it to be, even in mathematics. But that's not a bar to deepening our understanding of nature and the world we're in, and hopefully one another, and how to live with diversity. That is a major issue. And so there we're going off into social philosophy and moral philosophy. How do you institute a set of values that meets human needs? And those are very, very big topics. But philosophy, of course, gets involved in those as well. And so it could be that some of the results of philosophy of mathematics give us at least some ideals that we can strive for, right? Clarity, acknowledging what your premises are and which ones do you need for certain results. Similar questions to be asked on the social and political front. What kind of institutions and rules do we need to get good results that we agree are good results for our whole community or for multiple communities, right? We don't want the rules to be too strict. We don't want them to be too lax. How do we go about developing those rules and instituting them, right? So there's some similarity between, how do we get a system of ideas to work in a desired way, and how do we get a system of institutions made up of people with their complex abilities and needs to work in a desirable way. They're not totally unrelated. So philosophy could be seen as kind of idealized thought experiments about how to solve problems and how to construct interacting parts that you want to function in a certain way. So there, I guess one is talking about systems analysis and stuff like that. I think computer scientists think in those terms too. Anyway, I think that there is great value in looking at our ideas and how they can be made to work best for certain purposes. And so there are some similarities between these different areas. We're looking for the right level of description for our purposes. And we're looking for to get systems to work to meet certain goals that we set. And we need methods of adjusting those systems and making them better when we see that they don't work as well as we'd like. Maybe that's an optimistic note to end on.
No, that's good. Yeah, I like a lot of what you said there for sure. Especially what you said at the outset about look, it's really interesting stuff puzzles to look into, things to think about, and just some practical knock-on effects as well.
Right.
Yeah. Okay, so thanks so much for being here, Professor Hellman. I'll end the questions there. It's been really great having you.
Thank you so much for having me. It's been a pleasure, and I hope others are able to enjoy our back and forth as much as we have.